Okay, we were probably here. What we are discussing, that if TOD and FOD means third order dispersion and fourth order dispersion are planned to study, those will be if not planned to study actually. If we only would like to study the dispersion first order, second order dispersion and the nonlinearity, just to study the soliton. Okay, because soliton the dispersion will be balancing the nonlinearity. It will be giving us the generation for giving us the fundamental soliton. So if that is the case, then the equation will be becoming like this. Here the, th the this third and fourth order dispersion are absent. So here also we can study with this equation, nonlinear Schrodinger equation. Also we can study the nonlinear the soliton, the propagation and generation and propagation of soliton. What this group B will be doing for group B? What is the case? Let me take it. Yeah. Group for group B, to study only the nonlinearity induced SPM, means self-phase modulation, the dispersion part is not required because the self-phase modulation uh, 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 is a is a phenomena that arises due to nonlinearity only. So group velocity dispersion or third order dispersion or fourth order dispersion, we can take them zero, okay, straight away. So the equation will be becoming like this. So for group A, we have to consider beta 2 means dispersion. For group B, we may not be using the dispersion. Okay, so uh, this is the case. Let's see what we are going to, how we are going to have it. So these are the steps that we have to go with. First, we need to plot the imaginary real part of chi1 and also plot the real part of chi3. Here I am giving an example of real chi3, plotting of real chi3 with respect to in comparison to imaginary chi1. Here you can see, yes, here you can see, if we are applying this uh, that if when we are not applying this control field, then definitely there will be a very intense peak at delta p equal to 0 position, and when we give the omega c non-zero, means we are creating the EIT window, then it will be this the absorption will be reduced within this delta p equal to 0. Now how much it will be reduced? Say for example, we have taken a value like 0.2 into 10 to the power 20 10 to the power 12 second inverse, or zero point 0.2 here in this picture. If we take zero point 0.2, that will be equivalent to 0.2 into 10 to the power 12 second inverse. So at zero point 0.2 here, at this point, this is 0 we are considering. Let's say this is 0. 0.2 is very near to this is this 0 towards positive side. So here you can see that when it control field was not there, there was a very large value of imaginary I1, means absorption. So absorption value was very large at zero point 0.2 when control field was not applied. Now when control field is applied, a particular control fee is applied, say for example for mark 3, the graph mark 3, this graph. Here you can see the control this absorption is almost 0 at zero point 0.2. So that will be reduced by almost 10 times. Okay. Say for example, initially it was 2, now it is zero point 0.2. Okay. So that will be reduced by 10 times. That we are going to check actually. If it is the imaginary, sorry, the uh, what is called the absorption become smaller than it was before, then that is the success of applying to electromagnetically induced transparency. Now at that point, what we will see, we have applied omega c equal to some non-zero value. This window has been created for omega c non-zero, and this solid window is also created for omega c high value of omega c. So let us take the highest value of omega c that applied. Okay, for that highest value at point 2 value of delta p, the absorption become very small. At similarly, we are plotting chi3. In the chi3 also, you can see that this is for omega c equal to 0. This correspond to this peak. This is omega c equal to 2. This is omega c equal to 2. This window has been created because of omega c equal to 2, and this solid window has been created because of omega c equal to 4. Now let us consider only these two, omega c equal to 4, uh, imaginary part as well as real chi 3 part. Here you can see that absorption become very smaller, and at that point also we are having very large value of real chi 3 at somewhere at here. This is 0, we are considering this is 0. Okay, at this point, this is the point 2, and if you see the point, check the value of point 2 here, then also it will be certain value 10 to the power certain value of the order 10 to the power minus 11 or 12. Okay, that minus 11 or 10 12 minus 12 meter square per volt square is also very large value of real chi 3. That also can instigate the nonlinear parameters, like nonlinear phenomena like self phase modulation, cross phase modulation, soliton solitongenation, etc. Okay, now here coming to that this part now. Uh, from the plotting we can investigate those things. What are the values of beta 2, beta 3, beta 4, and uh, the value of w is that having a direct relation with chi3. Chi3 and w can be similar in nature, but that will be a value differ by some constant. Okay, w and chi3 are almost similar but differ by some constant. So here we have to go to search for particular set of parameters in nonlinear Schrodinger equation as discussed. Yes. Then okay, yeah, what group A will be doing? Group A will be doing this one. They will be checking whether dispersion and nonlinearity are opposite in sign or not. If opposite, go for numerical simulation with MATLAB. We will be discussing how this numerical simulation will be forwarded. Okay, in the next later class. And what group B will be doing? Group B will rewrite the nonlinear Schrodinger equation without the dispersion term and then go for the MATLAB programming. So rest part will be only to find the dispersion and the nonlinear terms at some particular point of delta p, such that our requirement is matched, and with those parameters of nonlinear Schrodinger equation will be going towards the MATLAB simulations. Okay, and those MATLAB simulation will be discussed later. Okay, now what will be the result, expected result? Expected results are as follows. uh, this is for group A. Group A will be having this kind of result. This is a pulse which at z equal to 0 means when it was a pulse has to be launched at z equal to 0. This is the length of this quantum well. Okay, and this part is this z axis giving us the distance of this propagation. and this is the distance of the quantum well. So when, and this is the tau. Tau means this time. This axis time axis, and this is omega p means the intensity. Now here we see that we have launched a 500, some value is there, some unit is there. Unit I missed to give here. This is just for an example, so unit is not required. We have taken up from 500 to 500 means 1000, say for example picosecond, 1000 picosecond pulse. So a 1000 picosecond pulse was launched at z equal to 0 at this point, and it propagate with that distance, and you can see that with that propagation also the pulse is not distorted. So if it is not distorted, then definitely that will be a soliton. Okay, if we, from our calculation, if we get this kind of pulse, then our result is met. Our task is will be finished. Okay, so we can say that later on we can say that if we are getting this kind of result, then we can say that which in this parameter, in this with this parameter in this quantum well, we can propagate a soliton, we can generate and propagate a soliton without any deformation. Okay, that will be our success if we able to do it, uh, uh, have this result. For group B, group B will have this kind of picture. This is the typical structure of self-phase modulation. In self-phase modulation, what happens? They are due to the pure effect of non-linearity, there will be a various production of pulses at the end of this quantum well system. Now, say for example, you have launched a pulse like this. This is a pulse which was launched at the initial point, means at the entry point of this quantum well. And this is the entry point of this quantum well, and this pulse was launched in this entry point, and during propagation this will be the structure of the spectrum. So now here you can see that at different wavelength, initially it was launched at around not 10 micrometer, and at the output what we are seeing, not only the 10 micrometer pulse, but also there are production of 1 2 3 4 5 in the left, in the right side, and 1 2 3 4 5 in the left side. So along with this pulse, along with this initial pulse, there is a production of 5 more pulses in the left side, 5 more pulses in the right side. So due to the non-linearity, we can say that due to the non-linearity has induced a new pulse generation, means generation of new frequency, which can be seen here in this picture. So 5 plus 5, 10 more plus pulses has been evolved, have been generated. That is the function of self-phase modulation. Okay, in self-phase modulation, uh, from one pulse we can get several pulses. Okay, so this pulse may be a single pulse of at a certain wavelength. Single wavelength pulse means this is a monochromatic light. From the monochromatic light, what we are getting? We are getting a band of lights. Okay, that is if this can be happening, then we will be succeeded in your classes, in this research also. Okay, so these are the two things we are going to do. Okay, so we'll be studying, we'll be discussing step by step. You uh, be in touch with me, and we'll be discussing very soon. Okay, okay, take care. Safe, be safe at home, and take care of yourself and your parents, and do not go out. The pandemic is expanding, and it is day by day it's become worse. Okay, take care. Okay, thank you so much.